I'll first quickly introduce the company. I've already been introduced myself, so I'll skip that. Sort of Innosen sort of started a long time ago. At that point in time, we were part of a company that you'll probably know better. It was Sencom. I was one of the owners of Sencom. We had an amicable split sort of about 7 years ago, where I was concentrating more sort of on 3-piece, Sencom sort of more on 2-piece. As I said, I will not introduce myself. I am an engineer, so perhaps what I say is too technical for some of you, but I'll try to limit. I'm going to talk about understanding curves, and don't let your fantasy sort of work too hard. It's all about process capability, histograms, statistics. And when you hear that, you're probably all going to shiver, because it's probably the topic that you hated most at university. Nobody that I know ever likes statistics, but I'm going to try and sort of explain it sort of in a way that you all understand, and that will make it interesting. First, the agenda. First, I'm going to talk about why we should be concentrating on this. Then I'll do a little bit of theory. I'll talk about the quality of the cans, quantity of the cans, give you some examples, and then conclude. First of all, why? Well, I've said this before. Of course, any company, it's all about the money. It's not because we love cans so much. Of course, we do, but we love money even more. So we are only in this can making to make sure that we sort of achieve the return on investment that our sort of shareholders need. Now, the return on investment for can makers is determined by a number of things, and if you do a sensitivity analysis, you will find that the most important things determining the return on your investment are the sales price of the cans. This is not something that we in the operational field can really influence very much. This is more about negotiation. It is the cost of the materials. Again, in the operational field, there's not a lot you can do about that. This is your purchasing department. This is how well they negotiate their contracts. And finally, there is the number of cans that you produce. That is something that is exactly sort of what we can influence. And that's where one company can distinguish itself quite dramatically from another. And when I say number of cans produced, it's not just anything that you produce. These need to be cans that are of commercial quality. Doesn't mean they all need to be perfect, but they need to be good enough so that your customers are willing to give you money for those cans. Because if they don't, you've produced scrap. Scrap is the most expensive product that you can possibly make, because you've invested all your metal, all your lacquer, all your labor, and you have to throw it away. You better not have started if you produce bad cans. So, just to make it a little bit sort of more sort of visible, as I said, both are important, but you want to try and hit that little smiley face in the end. I made a little graph here where you can see the months of the year. The first line here are the fixed costs, and these are quite arbitrary sort of lines. The next one is the sort of variable cost, and what I've done is I've put that on top of the fixed cost, so you get something like this. That then automatically makes your total cost. Now, almost all the can makers will work sort of for 10 to 11 months before sort of their profit sort of exceeds their total costs. This here is the profit that you make per can. So every can you make a little bit more profit. And as you make sort of more cans throughout the year, at a certain point, the total profit will exceed your total cost. This takes a long time, because it is per can, and in the beginning, as I said, your cost is higher. Now, if you are able to make more cans and sell them, then sort of that green area, which is the accumulated profit, actually increases. And it will look like this. And to be honest, you don't really need that much extra production to be able to double your profit. It is interesting to do that. First start, as I said, about the quality of the cans, because the quality is very important, and then I'll talk about the quantity. Quality. To be able to explain it, I need to explain histograms. Histograms is something that I sort of personally sort of hated, but I'll try and explain it. And I'm going to do it using flange diameter of the can, sort of as the particular criteria that I want to sort of check and influence. So what I'm going to do is I've got a whole pile of cans, and I'm going to measure each one of them. Now, of course, most of the cans, if I have a target of, say, 100 millimeters, hopefully most of my cans are going to be 100 millimeters. So what I'm going to do is I'm going to mark, for example, boxes on the floor, and this is the one where I put the cans that are 100 millimeters. Here I put the ones for 100.1, 100.2, and on the other side, the ones that fall a little bit short of my 100 sort of millimeters. So if I then sort of measure them and I start stacking them in those particular boxes that I've drawn on the floor, the 100 millimeter ones, they get the most cans, because that is sort of what I was trying to make in the first place. But you see there are also cans that are too big, that go towards, for you, the right of the screen, and there are cans that are too small, that are on the left of the screen. Now, interestingly enough, if you look at the shape that you've got there, and you put a line through it, you get this particular curve. This is often referred to as a bell curve. It's also called sort of a distribution sort of curve. And this particular distribution, and that's true for a lot of the things that we do in can making, has some very special sort of properties that were discovered by one of the greatest mathematicians ever, a German guy called Mr. Gauss. And you can see him in the 19th century. It's kind of humbling that he invented this, and we got difficulty getting a head around it sort of a few centuries later. But what he sort of came up with is a mathematical description of this particular bell curve. That's why they're also often called Gauss curves or Gaussian distributions. Now, as part of his theory, he developed this thing called the standard deviation. Now, what is that? If you go back to sort of this particular curve, and you draw a line sort of in the center of the highest peak, as I said, that was the value that we were targeting for. And you then start sort of putting a line on the left and on the right, and you see how many cans you've actually captured sort of that big pile. How many are now in between? If I cut it off here, cut it off there, how many, if I, for example, started with 1,000, how many have I got? Yeah. Now, if you move these lines further and further apart until you reach sort of 68%, and I need to press a few more times, until you've reached 68%, you actually have moved those lines out plus and minus 1 standard deviation. So this is how you can actually figure out what a standard deviation is. But that also means that there's other ways of determining the standard deviation out of the statistical data, sort of that you can gather from your production line, from your quality laboratory. But once you know what your standard deviation is, and you know that you go plus or minus 1 standard deviation away from the average, you've covered 68% of your production. If you go 2 standard deviations away, you've got 95% of the production. And you can carry on like this, plus or minus 3 standard deviations, you've got 99.7%. Now, that gives you the possibility to go further, and you then get a table like this. You go 1 standard plus or minus 1 standard deviations, 2, 3, 4, 5, up to 6. Everybody's heard of 6 sigma. What is this 6 sigma? You now move 6 sigma that way, 6 sigma that way. And to compensate for the long-term stability of processes, you actually subtract plus or minus 1.5 sigma. And what you then get, and that's in the 3rd column, is the DPMO. It's the defects per million objects. So you can see that if you indeed achieve plus or minus 6 sigma, you only have 3 defects per million cans. That is typically what is accepted by our customers. Yeah. So what we need to try and do is achieve sort of that 6 sigma. These are 2 examples of a distribution, just so that you can very quickly try to remember and interpret what it looks like. You can have a distribution which is very narrow and tall, or you can have one that's very wide and flat. In both cases, I said I started off with a sample of 1,000 cans. In both cases, I've got 1,000 cans. But in the narrow and tall curve, they're all very close to my average, to my target. Yeah? So that is actually a better process than the process that is long and wide. So narrow and long sort of is better than short and stubby. Yeah, just to remember. This one, yeah, this is where the process capability comes in. We all make agreements with our customers, and we say, we're going to supply you this particular quality level of cans, we're not going to have more than so many defects per million. What that means is that you need to make sure that your standard deviation does not move away more than so many standard deviations from the average. And that is where you will then define, for example, your lower specification limit. It's usually symmetrical, so then on the other side you have the upper specification limit. So this area under the curve are the defects. And if you've promised your customer this lower specification limit and that upper specification limit, all these are potential complaints, both here and on the other side. So you either need to get this distribution even steeper, or you need to agree a specification limit that is further out. Because if these are the quality data that you're measuring, and this is not what you've agreed with your customer, you just know that you can wait for complaints. You're not doing your job properly. Now, how are you going to improve this? How are you going to get there? The thing that some of you will have seen before is we typically do it by, if this is a particular step of the can making process, we take samples out of the process, we measure them, we then sort of determine what it should have been, it's not right, we make an adjustment, the process changes, and we just repeat this until we've got what we want. The number of samples that we need to take depends on how stable the process is. If we've got a cracky process that changes like crazy, you can hardly take enough samples to be able to get the process under control. The very first thing you need to do is get this process right. And then you can reduce your sample frequency and you can still have sort of a distribution curve which is really sort of narrow. So the choice that you have is to indeed keep on getting this sample, adjusting the process and going through the circle again. But that takes a lot of time, takes a lot of effort. So you can keep on improving, but you can't improve forever. If you, for example, take double sheets with a D-stacker on the coating line, yes, you can sort of course, you can adjust the vacuum, you can adjust the position of the sucker cups, you can adjust the surface area, you can leave it a little bit longer so that the doubles can fall off, you can do all sorts of things, but at a certain point you have to stop trying because you're spending so much money on trying to get that last double sheet that you're better off sort of not even trying that because there is a law of diminishing returns. On the other hand, you can't afford sort of to send doubles into your process, as Mark sort of pointed out. So there's two things here. This one I'll come to in a moment. For those particular instances where you can no longer afford to further improve your process because of the law of diminishing returns, you're going to need a gatekeeper. You're going to need a sensor that will simply measure sort of every single object, and if it's outside of the specification limits, you simply need to reject it. So give up on trying to improve the process further, because it's going to cost you too much money, too much time. Simply accept you can't get it perfect, but install a gatekeeper, because that is, economically speaking, in that particular case, the best solution. Now there's another thing. When I said we have a process, we take a sample, we compare it with what it should be, we adjust the process. Adjusting the process is something we need to try and minimize. Interventions in a can factory can be, I would almost say, lethal. The why people, the operators, and it's very unfriendly to say that, but they're very often the weakest link in our sort of process. We need to try and automate things. The operators don't come to work in the morning to deliberately do a bad job, but they make mistakes. If it's automated, the chances of mistakes slipping in are much smaller. Operators might have their mind somewhere else. Some of them might not even have a mind or a brain. It is very, very difficult to make sure that if you start allowing people to make adjustments on machines, to make sure they always do it correctly. You need to minimize the number of interventions, which means that this process control you need to automate as much as possible. Try to do away with any adjustments. Good. That much for the theory on quality. Now on the quantity. And I need to hurry on. I'm going to show you a process. Process 1, process 2, process 3. Every process has a limited efficiency. And I've assumed there's going to be 90%. Now, if these processes are, as we call, close coupled, if, for example, this thing could run 100% of the time, but it doesn't, it only runs 90% of the time. Well, process 2, if this one doesn't run 100% of the time, will only get supply 90% of the time, so this one can't run either. Yeah? When this one doesn't run, then if this one only runs 90% of the time, it stops, this one can't get rid of its product. So if you look at the efficiency of 3 machines in series, it's actually the multiplication of the efficiencies of the individual machines. So I have 2 that are 0.9, the efficiency of the 2 together is only 0.81. If I have 3 of them, it's only 0.73. And it very quickly, the bottom drops out of it. You have no production left at all. Now, how can you sort of improve the situation? And here I have one process that's 0.9, the other one is 0.7. The lower efficiency is typically the efficiency on what you would call your bottleneck machine. So what you do is you make sure your bottleneck machine is always provided with cans, so that it never has to wait for supply. You make sure that everything's pulled out very rapidly, but still you only have the 0.63. And if you now add a buffer, and in this case an infinite buffer, the efficiency is no longer the product of the 2, but it becomes the efficiency of the one with the lowest efficiency. So instead of ending up with 0.63, I've got this efficient, which was 0.7, and the difference between the 2 is 7%. So by adding this buffer, I actually gain 7% output of my operation. That's a huge amount of cans. That's the difference between a loss and a huge profit. Yeah. So having buffers in strategic places, like that nice rotary thing of sort of interlocks, or having a bright can sort of palletizer in front of your decorator, is absolutely essential. Yeah, the same in 3Ps, you need to make sure that before your welders, you have a very efficiently running slitter, and you need to make sure that you do not feed your welders sheets that have contaminated margins, because your bottleneck machine sort of will have a problem. This is just an extrapolation. If I have more machines, you see after 7 machines, I only have 50% of my production left. So it's really important to look at this. So you need to concentrate in this whole series of machines, or your bottleneck machine. How do you find what that is? A lot of people do this with software, but otherwise it's generally quite well known which those machines are. You need to concentrate on improving your bottleneck machine. You can, of course, concentrate on trying to improve an arbitrary machine somewhere else in the line, but that's not going to have the same effect. You might spend lots of dollars there, you're not going to see a penny of extra profit. You need to concentrate on your bottleneck machine, and you will immediately notice sort of that your total production increases. So concentrate on your bottleneck machine, surround it with buffers. Use the fault mode and effect analysis sort of both to improve your quality and your quantity. So now, very quickly, and this is going to be the advert bit, and I've got exactly 50 seconds left. So what I'm going to do is going to quickly talk about a few of these gatekeepers that we've got. We've got a double sheet detector, and we have sort of a margin inspector. This is a double sheet detector. It was developed sort of at the request of, at that time, the world's biggest sort of can maker. They wanted to get rid of the interventions. They didn't want a double sheet detector that was adjustable. So this one doesn't come with a control box. There are no settings, there's no buttons, you can't do anything. It just works by itself. Yeah. So no intervention whatsoever. There's no change when you change from aluminium to tin plate, to copper, to, it doesn't matter. It works with any metal, works with any thickness, no adjustments, no buttons, just works. Oldest ones are now working for more than 20 years. don't seem to break. Next one, plane margin inspector. This is meant to go on the slitter just before the welder. Why? All the welders, of course, they have weld monitors, but unfortunately not all the defects sort of are detected sort of that reliably by weld monitors, and they still burn the weld wire. By fitting this on the slitter, and you can see it sort of sitting here, there's no sheet underneath it at the moment, but you can see it sitting here, you can detect sort of any contamination sort of in the margin, and it will just stop the slitter, or you can automatically, if you can sort of find a way of doing it, you can automatically reject. Most people stop. It also detects skewed sheets, or sheets that were skewed sort of on the lacquering line, or that were sort of moved sideways, that translated sort of on the coating line. Picks those up as well because the margin's simply not in the right place. Pressing the wrong button. Mention one quickly for sort of the process improvement. This is the Skew measurement system used by, I would say, virtually every can line sort of in Europe. It's also in South America, quite a few. Also some in Thailand, thank you sort of to the Thai customers. This one measures the skew of every single sheet, and you can adjust sort of what tolerance for the skew that you allow. The moment it's either too small, too big, it stops the line, or if you have an automatic rejection, you can reject it. What is it used for? I would say specification verification. What is that? A lot of people buy a coating line, spend more than $1 million on it, and they have absolutely no way of checking that what they get delivered meets their requirements. You would normally specify sort of what your long-term stability is for the sheet handling, but you've got no tools to measure it. This is only a few $1,000s, and then you'll know whether you actually got what you paid for. So the first thing you need it for is specification, verification. After that, it will help you with the preventative maintenance. This one actually, because it really measures every sheet, it gives you a standard deviation, the one that you need to be able to know if your process is in control. You can help it with the adjustment of the dogs, the speed up programs, and it is also a gatekeeper in case you do have one that's out of spec. This is how it's installed. It goes on many, many different coaters. We've sold hundreds of these. There's an option sort of for this to also have a sort of a check of the sideways movement of the sheet, also for the registration that it moves into the rollers at the right amount of time. I'm just going to step through this quickly. So this is the end of it, the conclusions. As I said, both the quality and the quantity are equally important. You need to make good cans, you need to make them in sufficient quantity to make sure that your investment reaches that return that you need. You need to identify sort of what the bottleneck machines are. And when it comes to the buffers, you need to surround your bottleneck machine with the buffers to get the maximum gain in efficiency. The sample, measure, improve, and start all over. Yes, it's a good start, but because of the law of diminishing returns, you have to stop at a certain point in time and move over to the gatekeepers. Ladies and gentlemen, that was it. I'd like to thank you very much for your attention.